Hello friends, good afternoon. Let's start our today's class. As usual, I hope to see your faces first. And while you are turning on your cameras, as I promised, from today, if I don't see your faces, that you are not present on the lecture. So let's briefly remind ourselves what we covered last week, and I need to finish that topic to comment on the last slide. We spoke about conditional probability. I hope you had an exercise session on this topic, and I hope you had an intensive study during that time. So basically the idea of conditional probability is the following. If you know that some event happens, then we can update our calculation of a probability of another event. And so we define the conditional probability formally. Based on this conditional probability, we basically formulated several things. So one was the law of total probability. So how to calculate the total probability of some event if you know the conditional probabilities of kind of parts of this event happening given that something else happens. So we had some examples here, and the most important application of this conditional probability concept is a bias rule, which allows you to calculate the conditional probability of some event if you have the kind of knowledge about the opposite. When event A, conditional on B, happens with some probability, then you can reverse and calculate the probability of B happening given A. So that's an important idea of bias rule, and I showed you several examples how to identify what's the probability that the person is liar, given that the polygraph test says that this person lies, or probability that the person is not a liar. And also we had some application to the COVID tests that also gives us some kind of striking result, that even though if the test says that a person is infected, the probability that the person is indeed infected is only 16%, which is quite low probability and quite low reliability of this test. So the last point here that I want to comment on is the independence of events. So this is an important concept. We are going to use this concept throughout all our sequence of courses: probability, statistics, then econometrics, then econometrics 2, for those who will survive. So the independency means the following. So two events are independent if the probability of their intersection equals to the product of their probabilities. So that's precisely. So first of all, we know that there is an intersection of these two events. So these two events are not disjoint. They must be, at least they must have something in common here. And if these two events are independent, then their intersection, probability of their intersection is simply the product of their probabilities. So we would say that two events are independent if knowing that one had occurred gave us no information whether the other had occurred or not. So we can reformulate this in a way that probability, conditional probability of an event A given B is simply equal to the unconditional probability of an event A, and vice versa. Probability that event B occurs is given A is simply equal to the probability of an event B. So let me give you a practical application of this concept of independence, why I'm saying that this is very important and why you need to believe me about this. We use this idea of independence usually when you do some surveys. For example, you want to know how people on street, so which political party these people support, let's say. How should you design your survey in a way that you can believe the results of this survey? So your experiment will be in random selection of a person and asking this person which party this person supports. And now, how you can verify that this is indeed random? If you, for example, stand in front of the university and ask all the people who go out from the university, this is not independent. Why? Because at least you can predict, given one observation, what will be for the next observation. You can predict, well, you can probably cannot predict the, let's say, which political party this person supports, but you can predict other characteristics of this person: age, education, something else. Because well, I'm standing in front of the university. I know that I probably expect more younger people to come from this. And that's it. This is not independent survey. That's why you cannot trust to the results of this survey, for example. Because you can predict, given one student who came out of the university and told you something, you can predict, you can update the probability that another student will tell you something. What will be the really independent random sample? Just randomly generate telephone numbers and call these telephone numbers without any knowledge who are these people. You don't know gender, age, political preferences, income of this person. You know nothing if you really independently, randomly generate the telephone numbers and then just call these telephone numbers. That's how it works. And usually these kind of surveys on street, they are not that independent because they might be influenced by the location. So we know that if we go to some working district, we would probably expect to see people with a lower income, and we can predict by this lower income which political party these people would support. If we stand in front of the some trade center, shopping mall, we also can predict something about these people and so on. So this is not an independent thing. So that's why the idea of independence is important when you do some practical things, when you're collecting some data to make some predictions and or to make some forecasts, or simply to explain the some let's say some political or like economic situation in the country. Okay, so this formally, where this comes from, since we know that the conditional probability is defined as this fraction, as the ratio of probability of A intersection B divided by B, and we know from the definition of independence that probability of A and B happening simultaneously is simply their product, and we just cancel probability of B and we have PA. So that's where this relationship comes from. So the unconditional probability equals to the conditional probability. So an example of independence. How should we verify that two events are independent or not? So a card is selected randomly from a deck. Let A denote the event that it is an ace, and D the event that this is a diamond. Knowing that the card is an ace gives no information about its suit, right? So we cannot tell, well, if I know that this is ace, what's the probability, what's the suit of this card? So formally, how can we check that these events are independent? So what's the probability of A? What's the probability to draw an ace from the deck? It's 4/52. We know that there are 4 aces. We know that there are 52 cards in total. That's why probability to take ace from the deck is simply 4/52. Now, how many diamonds do we have in a card deck? So we know that each suit is represented by like there are 4 suits, right? So that's why it's 1/4 simply, or like 13/52, which is the same. So now A intersection D is the event that the card is an ace of diamonds, and P A intersection D is 1/52. So this is one particular card out of 52 cards in the deck. So now, does this relationship hold? Does this relationship hold? PA times PB equals to PA intersection B. So let's see. So PA times PD, here it's 1/52, and this is exactly equal to 1/52, which we calculated directly, knowing the intersection of A and D events. So it proves that 2 events are independent. Kind of when you take a card and somebody tells you that this is ace, so the probability that this is ace of diamond, probability that this is diamond, conditional probability is still the same 1/4 as an unconditional probability to take simply a card of diamond from a deck. And the extension of this idea is the mutual independence of events. So the mutual independence, when we extend from 2 events to n events, or to m, so to n events, then we should be able to do the following. So we need to take a sub-collection of events of size m, meaning that we are not taking all events, all n events, but we can take some part of them, and then for this part the same story holds. So the probability of their mutual intersection is the product of their independent probabilities. So for example, a fair coin is tossed twice. A denotes the event of heads on the first toss, B the event of heads on the second toss, and C the event that exactly one head is thrown. So if we toss a coin twice and heads on the first toss have the probability 1/2, heads on the second toss is also 1/2, and exactly one head is thrown is also 1/2, right? Because it's either head tails or tails head. So all probabilities are the same and they equal 0.5. So now, look, what is the probability of their intersection? So intersection means heads on the first toss and heads on the second toss, and only one heads on 2 tosses, which is 0. It's not possible to have all 3 events simultaneously, right? You cannot have heads on first toss and heads on second toss and one head only. It's not possible. So probability is 0. But the product of probabilities is 1/8. So these events are not mutually independent, because if you have heads on the first toss, then you know that event C already occurred. and you know something about this event C. So that's a simple example about the mutual independence. So overall, once again, independence simply is checked either by this condition or by this condition. So both are telling us about the independence. So I explained you the practical application of independence whenever you want to have a solid and trustful results of some survey or from the data collection. If you do some research and you want to collect the data and you want to claim that this data is reasonable and your results are trustful, then the only way to do this survey is to perform the random sampling, which is based on the idea of independency. So each observation in your data must be really independent. And as I said, we will use this idea of independency later on in statistics and econometrics, and we will usually test whether it's whether this holds or not. And so here are some examples how you can check this independency formally. So any questions regarding this independency? Should be more or less
No
simple.
question.
Okay, perfect. Then one announcement from my side. So this is already the 5th week, and by this moment you don't have any points, and this is probably not fair. So that's why we have 2 home assignments on the course page. So both home assignments, so this is the home assignment 1 on this topic set theory, this is home assignment 2 on this topic probability. I believe that they're kind of not that difficult. They are based on the material that we discussed during those two weeks. So they both start tomorrow, and you have 1 week till Friday midnight to finish them. They work exactly in the same way as for microeconomics. So you are familiar to the way how these home assignments look like. Several tasks, usually 4 calculations. You provide the number as an answer, then it is automatically checked by the machine. If your answer is correct, you are given some points. If your answer is not correct, you wait until the end of this home assignment, until Friday midnight, to see the suggested process of the solution and to see the answer, and to then you can write me if your solution has been correct or maybe had some small mistakes for me to manually grade. So during the next week, I will also make home assignments for these 2 topics, counting and conditional probability. So we will make up and you will start collecting your points for the home assignments. Also, I put here the solutions for your exercise sessions. So these exercise sessions are kind of, so they have all exercises that suggested by me to be solved, and these solutions are made by myself, so maybe they would be slightly different to what you have in your exercise sessions, but I hope that answers are more or less the same. So that's why if you have some confusion from the exercise sessions, if you probably missed something, so you can find it here. So, any questions about home assignments? I think this is familiar to you and shouldn't be that confusing. Okay, so then we move to the new topic today, and this topic starts the essential part of all of our future sequence of subjects. So we start to speak about random variables, because random variables are... Yes, Ekaterina.
Sorry to interrupt you, but can you find this lecture somewhere in Moodle or something else?
Here. So they are put here. All slides
okay,
are...
all 5 lectures, yes?
All slides are available exactly in that way that I'm showing you. So they're here.
Okay, thanks.
And today's lectures is also here. So it's already here. As for microeconomics, everything is available. I can put it with some delay, probably sometimes, but usually they are there in advance. Okay, so discrete random variables. From now on, we will concentrate mostly on these objects, on the random variables. We will discuss their characteristics. We will discuss how to use the concept of random variables in some practical applications. First of all, we need to understand how this works from the theoretical side. So first, let's define what is random variable. So we have a random experiment. Consider a random experiment with a sample space omega. So that's what we already know. We make some experiment, we list all possible outcomes of this experiment, and this constitutes a sample space omega. So now we define a function x, and this function x assigns to each element in omega one and only one number x of omega, which equals to some small x. And this function is called a random variable. So look, this is something interesting and probably something surprising. A random variable is a function. This function transfers events inside a sample space, translates these events into some numbers, and to each event we have corresponding one and only one number, which we denote with this small x. And we kind of convert the whole sample space from events, from the kind of oral description or from the verbal description into the numeric description. So now we have the following. So the space or range of x is a set of real numbers. So real numbers d, such that for each number x, we have this function of omega, where omega, small omega, is in the sample space. So probably it looks ugly and it looks kind of confusing, but now let's see the example, and you see that this is very simple. So our well-known example, a coin is thrown 3 times and the sequence of heads and tails is observed. So we have a sample space for this random experiment. In this sample space we have 8 objects, and each object is denoted with this small omega. So small omega is this HHH, or small omega is HHT, and so on. So now we define a function x in the following way. So one example, x is the total number of heads. So what it means, I'm taking this small omega and I'm saying, okay, this is 3, right? So I convert this small omega into number 3. This is 2, this is 1, this is 2, this is 0, this is 1, this is 2, and this is 1. So I kind of translate all these events into the sample space from letters to numbers. And what do I have? I have a random variable x that belongs to a set of 4 possible outcomes: 0, 1, 2, and 3. Right? To each of these events, I have associated number from this range. So another example, random variable y, the total number of tails. The same story. I look at each event, I calculate how many tails do I have there, and I have also four possible outcomes, 0, 1, 2, and 3. Or z is the, let's do something more fancy, that is the number of heads minus the number of tails. So here I have 3 heads, 0 tails, so z equals 3. I have 2 heads, 1 tail, so z equals 1. I have 1 head, 2 tails, z equals -1, and so on. So I continue doing this. So overall I have 4 possible outcomes, -3, -1, 1, and 3. So look, I can have only one random experiment, and to this random experiment I can associate many different random variables. So once again, going back to my example about the random sampling and about survey. So for example, our random experiment is calling to some random number, telephone number. So I'm selecting some telephone number at random and I call there. So this is a random experiment and the outcomes are all the people who are clients of some telephone company. At least you can know, considering the first 3 or 4 digits in the number. But then look, what might be the random variable? Well, random variable can be the age of this person, the weight of this person, the working experience of this person, maybe how many years of education this person has, or something else. So we have a lot of possibilities, a lot of possible random variables that we can define associated with only one experiment. Select a person at random, call to this person and ask this person some question. Okay, so is this clear what the random variable means and what the random variable does? Nice, let's move on. So what is a discrete random variable? What are we talking about? A discrete random variable is such random variable that can take on only a finite or countably infinite number of values. So what finite or countably infinite means? An example. So x, the total number of heads when a coin is thrown 3 times. There is a finite number of possibilities, 0, 1, 2, and 3. So full stop. We cannot have 4, we cannot have 100, we cannot have -5 or something like that. This is a discrete random variable with a finite number of values. What does this mean, countably infinite? Let's define y, the total number of tosses until a head turns up. Well, do we know how many times should we toss a coin until a head turns up? It can be 1, it can be 2, it can be 3, but it can be 1 million if we are very lucky. 1 million is also possible. So that's why it's going to be countably infinite number of values. So from 0 to infinity, but we can count, right? We can count all these events, even though they go to infinity. So these are 2 examples of a discrete random variable. Now, we define a very important concept associated with the random variable. So first of all, the probability that x takes on the value small x is defined as the sum of the probabilities of all sample points in omega that are assigned the value x. So we know this is simple. If we know that this small x is associated with some events in an omega, then we can simply calculate this probability, and we will denote this either p that x, large X is a random variable, equals to small x is some particular number, or we can use this notation also px of x. And the probability distribution for a discrete random variable can be represented by a formula, a table, or a graph that provides this probability for all possible x's. So kind of distribution means that for each possible x, you need to associate the respective probability. So let's see. We have this example. And now let's try to understand what is the probability distribution of a random variable x, that is the total number of heads. So first of all, if we have an event TTT, x is 0, and we know that probability of this event is simply 1/8. So how do we know this? Because for this small x, 0, only one event is associated from the sample space, and there are 8 of them in total. So that's why the probability that x equals 0 is 1/8. Now, x equals 1. Oh my god, so some... Okay, so I hope you understand that this is the same line. X equals 1. We have 3 possible outcomes in the sample space that are associated to this value of a random variable, HTT, TTH, and THT. And the probability of x equals 1 is 3/8. So the same story for x equals 2 here, and for x equals 3, it's out of the slide, but okay, I hope you understand that there are HHH and the probability is 1/8. So I will update these slides on the page so that you can see the whole table. So that's a simple thing, right? You find how many events are connected to this value, and then you simply build this table, and with the help of this table you see the whole distribution of this random variable. So then another important concept, which is called the probability mass function. So if we have a random variable x, discrete random variable, and we have a space D for this discrete random variable, then we can define the probability mass function. And this probability mass function is simply the function that assigns probabilities to the values of our random variable for all x's in this space. So we should have two properties for this probability mass function. First of all, the value of this function should be greater than or equal to 0 and less than or equal to 1. So this is something natural from the definition of probability. And sum of all probabilities for all x's in this in the space must be equal to 1. So if you want, this is something that comes from these axioms of probabilities, right? Look, probability of omega is 1, and this is associated to this property. Sum of probabilities for all x's is 1, because this is the same naturally. And this probability of A is non-negative, and this left side of the inequality is exactly associated to this idea. So for the previous example, what is the probability mass function for x, which is a total number of heads? It's simply 4 possibilities. P of x equals 0 is 1 over 8, P of x equals 1 is 3 over 8, P of x equals 2 is 3 over 8, and P of x equals 3 is 1 over 8. So that's a probability mass function. We associate some probability to each value of x. And this is the graph of this probability mass function, so we can also define the probability distribution with the help of this histogram. So we have 1, 2, 3, 4 possible values of x, 0, 1, 2, and 3. And the height of each column is represents the probability, right? So 1 over 8, it's something like 0.125, which is here, and 3 over 8 is 0.375, I believe, which is here. That's a visual representation of this probability distribution. And one more thing that we need to know is the cumulative distribution function. So what's the difference between probability mass function and cumulative distribution function? If you have a random variable x, then cumulative distribution function is defined in the following way. Look, this is the probability that x takes values from minus infinity to small x including. So that's something different to the previous one. Look, or in the other way, it is defined as the probability that x of small omega is less than or equal to small x. Anna, what's going on? I see that there is your friend, right? Making selfies on your camera. Anna. Okay. So we usually shorten this second part of the equation to the following. So it's a probability that the random variable x is less than or equal to small x. So that's the way how we will usually write down this long expression. So once again, an example. First of all, f of x, like this cumulative distribution function, it should be defined for all x's for all real numbers. Even though x is a discrete random variable, still we need to define it for all real numbers because I can plug here anything. And the cumulative distribution function is non-decreasing, and it satisfies the following properties. If x goes to minus infinity, this function is 0, and when x goes to plus infinity, this function equals 1, which is also natural because probability cannot be less than 0 and cannot be greater than 1. So it is simpler to see what is cumulative distribution function based on an example. So remember, we had this example that random variable x is the total number of heads when a coin is thrown 3 times. And we have this probability mass function. We know probabilities of each possible outcome. So now, what is the CDF for this function? Look, first of all, f of x is x. This function is divided into several parts. So first of all, when x is less than 0, probability is 0. For this interval, for any number from this interval, probability is 0. Now, for any interval from 0 including, from any number from the interval from 0 including to 1 not including, this function equals to 1 over 8. For any number in the interval from 1 including to 2 not including, this function is 4/8. Look, it's not 3/8, it's 4/8. Why? It's cumulative, right? So I'm taking 0 plus 1/8 plus 3/8, and it gives me 4/8. Because this function shows me what is the probability that x is less than or equal to some number within this interval. Then this function for x within the interval from 2 including to 3 not including is 7/8. And finally, for any number that is greater than or equal to 3, this function is simply 1. Right, so that's the way how we define the cumulative distribution function. And the graph of this particular function looks like the staircase. So for any number of for any value of x which is less than 0, it's 0. Then at 0 it makes this jump to 1/8. And then for any number between 0 including and 1 not including, this function equals to 1/8. Then at 1 it makes another jump right to 1/2. Then from 1 and 2, between 1 including and 2 not including, it is equal to 1/2. Then at 2 it makes another jump. Then it goes to 3, and then it's 1 for any number greater than or equal than 3. So we simply accumulate all probabilities from PMF to get this. Well, it came to my mind, guys, one important thing, that I made a mistake here. Basically, I needed to write down the following. So it should be not. So we don't need the left side of these probabilities. It should be probability that x is less than 1, probability that x is less than 2, probability that x is less than 3, and so on. So I will in an updated slides on the web page, I will delete these parts because these parts are not needed. Yes. So the correct way to write down is the following. Let me correct myself. So the correct way to write down this distribution function is this.
Also about the last probability, is it more than 3 or equal or less?
More greater than or equal to 3. Yes, this is correct. This must be non-strict inequality. That's correct. But once again,
shouldn't it be less or equal?
No. Okay, so once again, let me write down this function in the correct way. So this function, so find these cases. Okay. So okay, so basically I need to write the following. So it's 0, 1/8, then 4/8, then 4/8, then 7/8, and then 1. And now I can define for which intervals of x this holds. So this is for x, which is for all x's that are less than 0. This is for x between 0 including and 1 not including. So this is the way how I needed to write down this function. This is for x between 1 including and 2 not including. This is for x between 2 including and 3 not including. And finally, 1 is for all x's that are greater than or equal to 3. And now, if we want to know how to calculate these exact numbers, like this 4/8, 1/8, and so on, we can write the following. So what is this function for all numbers up to 0? This is exactly the probability that large x is, let me write it here. So this is the probability that large x is less than small x, less than or equal to small x, right? So look, if I take any number, which is less than 0, so for example, for this case, I will take the probability that the total number of heads in 3 coin tosses is -1, is less than -1. So what's this probability? I know that this probability is simply 0. So that's why my cumulative distribution function evaluated at -1 must be defined as probability that x is less than -1, and I know that this is 0. Now, I should be able to plug there any number. So for example, if I plug there 1.5, so what is the probability that the total number of heads is going to be less than or equal to 1.5? This should be not strict inequality. So I know that there are only 2 possibilities. So this is the probability that x is 0 plus probability that x is 1, right? In this interval, x is less than or equal to 1.5, I have 2 possible outcomes from my experiment. X is 0 or x is 1. And I know that for x is 0, it's 1/8. For x is 1, it's 3/8. In total, I have 4/8. And basically, for any number within this interval, from 1 including to 2 not including, I will always have these 2 probabilities within this calculation. Or if I want to evaluate this function at the point of, let's say, 2.7, what should I do? I should remember that this is defined as the probability that x is less than or equal to 2.7, which is what? I know that inside that interval, x is less than or equal to 2.7, there are 3 options. This is 1, this is the second, and this is the third. There are only 3 values of x that satisfy this inequality. And therefore, I calculate this as 1/8, 1/8 plus 3/8 plus 3/8. So each of these probabilities, and in total gives me 7/8. Okay, yeah, so that was a short digression. So I didn't need to put these probabilities here. I needed to leave only these inequalities. So basically 0 for x less than 0, 1/8 for x within this interval, and so on. And this is not correct. So this is the correct way to define this function. So sorry for this confusion. I cannot even tell why it happened, but you see that you see how should we work with this function, I hope. Okay, is this clear? How do we use this CDF? The main idea here that CDF should be really defined for any number. So you are able to take any x, -100, 1000, 1 million, whatever. and you immediately should be able to give the value of this probability that your random variable is less than or equal to a given number. So for most of the cases you will get either 0 or 1, but there are several steps that are defined here. Okay, so now we move to the examples of some particular distributions. So there are some standard situations that we can encounter in practice. And for those situations, we usually have some nice predefined probability distributions. And now we will discuss several of them that are applied to the discrete random variables. And the first, the simplest, is a Bernoulli distribution. So first of all, definition. So what is a Bernoulli experiment or Bernoulli trial? So this is a random experiment, the outcome of which can be classified in but one of two mutually exclusive and exhaustive ways. For instance, success or failure, female or male, life or death, non-defective or defective product, something like that. So you have some random experiment, and from this random experiment we have only two possible outcomes. This random experiment is defined as a Bernoulli experiment. For example, let x be a random variable associated with the Bernoulli experiment, and we define this as follows. So if there is a success, then x equals 1. If there is a failure, then x equals 0. So for example, you throw a coin and success is heads and failure is tails. Then you define this variable as 0 or 1 in the following way. And so probability mass function of this variable can be written in the following way. So it's small p. Small p is the probability of success to the power of x. And you see that x takes only two values. It's either 0 or 1. Multiplied by 1 minus p to the power of 1 minus x. If x is 0 or 1, and otherwise it's 0. So this is something simple, even though the function is written maybe in slightly complicated way. But once again, so let's try to understand how this works. Well, let's say, I don't know, the probability of I don't know, what do we have? Randomly choosing male from a population, let's say, is 0.45, and we will define this as a small p. Okay, so and now look, so define, let's say, x as the Bernoulli variable, what's wrong, Bernoulli, correct, the Bernoulli variable such that small x equals 1 if, let's say, if male selected, and x equals 0 if female selected. So it doesn't matter, so we can define this as 0 for male and 1 for female. And now the probability mass function is going to be the following. So I need to plug this number 0.45 into the probability mass function here, and then depending on x, I define whether so what's the probability of x to observe x. So I have 0.45 to the power of small x multiplied by 0.55 to the power of 1 minus x for x 0 or 1 and 0 or 1 and 0 otherwise. So which gives me the following. What is the probability? What is the probability to select female, let's say? And I can translate this question like male or female into the language of numbers. So it means that x is 0. And therefore, my probability mass function simply is evaluated as this. And I plug it here and look what I have. 0.45 to the power of 0 multiplied by 0.55 to the power of 1 minus 0, which is 1, and I have 0.55, right? So what is the probability to select male? So my random variable is 1, I evaluate this at the point of 1, and I simply have this 0.45. So it might seem like unnecessary complication. You may say, well, why should we have this? I mean, it's simply 0 or 1, and it's simply two probabilities. Why should we have that complicated expression to define this probability mass function? So I would tell you that if you want to mathematically model this situation, or like, I don't know, you probably write some computer code for such a situation, you definitely need to have some mathematical expression to model this. So that's why sometimes we really want to know this probability mass function, and we will have this function in future for some practical applications. So it looks maybe a bit difficult, but you see that it works in a very simple way. So now, an extension of Bernoulli distribution is the following. So this is basically more interesting case, and it is widely used. The binomial distribution. So suppose that n independent Bernoulli experiments are performed, where this n is a fixed number, and each experiment results in a success with probability small p and a failure with probability 1 minus p. That's exactly as the previous one. The total number of successes is defined as a random variable x. So look, now x shows me the total number of successes, which means that this is a random variable, discrete random variable, because total number of successes is a natural number. It's 0, 1, 2, 3, 4, 5, 6, 7, and so on, up to n. It's finite also. And this total number of successes is defined as a binomial random variable. And for this binomial random variable, we have only two parameters, small n, how many repetitions do we have, and small p, which is the probability of success in one particular experiment. And the probability mass function is defined in the following way. So this is a binomial number. I hope you remember this from the counting topic. So let me show you. How do we calculate? Yeah, so it's here. So it was in combinations, right? So this number is calculated in a way, in this way. And so this is exactly the combinations of x from n. And then we multiply this by something that looks similar to Bernoulli distribution, but now we have, instead of 1 minus x, we have n minus x here. So let me give you a small example before we go to this, because this is probably a little bit complicated. We need to apply this formula, but I want to describe you how you can easily build this formula and understand how this works. Let me open Excel. And let's define something like this. Let x be a number of days when, well, I don't know, Gazprom's stock price increases. Something like this. So it may increase, it may decrease, right? So let x be a number of days when the stock price increases. Let small p equal, let's say, 0.55 be the probability that Gazprom stock price increases in 1 day. Now, let n equals, let's say, 4, let's do 5 days. And now, if you want to build a probability distribution for this random variable x, we need to do the following. So what is x? X is either 0, 1, 2, 3, 4, or 5, right? So the stock price can increase in 0 days, in 1 day, in 2 days, in 3 days, 4 days, or 5 days, because in total we have 5 days. So now let's try to think in a way that we used when we defined these random variable probabilities. So let's first think about events. So which events are associated with 0 increase? So it's decrease, 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 right? So 5 times decrease. It's kind of simple. So what is the event that associated with 1 day of increase? It's increase, decrease, 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 or decrease, increase, decrease, 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 or, and so on. I think you understand the logic, right? So there is only one increase here. So when there are 2 increases, there is increase, increase, DDD, or increase, decrease, increase, DD, or, and so on. So you understand the logic. And now let's remember the counting. So are we interested in the particular order of these increases and decreases? No, right? So for us, it doesn't matter. That's the same IDDDD or DIDDD also, or something like this. So we don't not care about the order. We want to have 1 decrease or 1 increase out of 5. And here we want to have 2 increases out of 5. And this should remind you about the combinations, right? In the combinations, you do exactly this. You calculate how many increases you have out of 5, or how many, like these 2 increases you have out of 5, and so on, right? So that's why in this calculation we exactly use this thing. Okay, so that's one story. That's why do we have this n over x, so count. Let's say we do this. We have the factorial of 5 divided by the factorial of 5 minus this number multiplied by the factorial of this number. Okay, we have 1 here, we have 5 here, 10 here, 10 here, 5 here, and 1 here. So that's the number of all possible combinations of this I within 5, all these 2 I's within 5 days. This should be clear. If you remember counting, this should be clear. Why do we have this count? So now, what is the probability of one particular outcome? What is the probability of one particular outcome? Of any outcome, right? So we need to know how many of them do we have in total, and then we need to calculate the probability of one particular outcome. But that's what, look, for example, for DDDD, if all of them are independent, so what is the probability of this DDDD? We need to take probability that stock price does not increase, which is 1 minus 0.55, right? 0.45. And we need to multiply this by itself 5 times, or simply to the power of 5. Okay, so that's the probability of this outcome. So now what is the probability of IDDDD, which equals to the probability of DIDDD, which equals to any other probability when we have only one increase, right? So it's going to be DD, IDD, and so on. What is the probability of this outcome? I should take 0.55 one time, and I should multiply this by 0.45 4 times, because I have 4 D's and 1 I, which is here. Multiplication principle, right? What is the probability of DIIDDD, which is equal to the probability of ID, ID, IDD, and so on? The same approach. I should take 0.55 probability of one increase, multiply this 2 times by itself, and multiply by 0.45 3 times. And look, this is this part. This is this part, p to the power of x, where x is 0 or 1 or 2 or 3 or 5, multiplied by 1 minus p to the power of n minus x, where n is 5, and when x is 0, it's simply 5, or then 4, then 3, and so on. So this part measures a probability of one particular outcome under each potential value of x. So I have this small probability, not small, but let's say probability of one outcome, which is 0.55 to the power of x, multiplied by 1 minus 0.55 to the power of n, which is 5 minus x minus 0. And then I have these probabilities of one outcome in these collections of events. And now I'm able to calculate p of x, which is just this probability multiplied by the number of these events. Voila, so I have this probability distribution. And we know that the probability distribution should satisfy one of the properties, that the sum of probabilities must be equal to 1. So sum of p's, let's check that everything works. Sum of probabilities is exactly 1. So everything is calculated correctly. Right, so what is this, for example? So probability that the Gazprom stock price will increase in 3 days not consecutive days, but just 3 out of 5. Maybe today, then tomorrow it will decrease, then 2 days after it will also increase, and so on. So probability that Gazprom stock price will be increasing 3 days out of 5, it's 33%. 4 days it's 0, like all 21%, right? And 5 days out of 5 it's just 5%. Okay, so that's how we can apply a Bernoulli, binomial distribution to some particular situation. And here you see the explanation. Why do we have exactly this formula? Why do we have this binomial number here? Why do we have this product of probabilities here? So I think we can skip this example. This is something similar. We have some disease and we have some probability, but I showed you more, let's say, extended version of an example. So the lecture slides are on the board. So basically you can see this example yourself. So next distribution of discrete random variables is a geometric distribution. So a geometric distribution is based on the Bernoulli distribution, and also it's something similar to the binomial distribution. So look, the geometric distribution is constructed from independent Bernoulli trials, but from their infinite sequence. On each trial, a success occurs with probability p, and x is the total number of trials up to and including the first success. So if x equals to the small x, then there must be x minus 1 failures followed by a success. So what does this mean practically? Let's go back to this example about stock prices. Let's now define x as the number of days before Gazprom stock price increases. So it may kind of decrease 1 day, it may decrease 2 days, it may decrease 3 days, 4 days, and so on. So x is going to be a random variable that describes the number of days until the first increase in the stock price would occur. Right? And then we will have exactly the geometric distribution. X minus 1 failures, and on the day X, there is going to be a success. And random variable X has a geometric probability distribution if and only if we have this probability mass function. Look, this is even simpler. You should have X minus 1 consecutive failures, and the logic of this is the same as the logic for the binomial distribution. So you need to multiply 1 minus p, x minus 1 times, and then the last day you have a success with probability p. And x here starts from 1 because, well, 0 cannot be applied here. Okay, and this is infinite, countably infinite discrete random variable. So, an example here. Suppose that the probability of engine malfunction during any 1-hour period is p equals 0.02. Find the probability that the given engine will survive 2 hours. So look, now the success is defined as a malfunction, so the engine should be broken. And if you want to find the probability that the given engine will survive 2 hours, it means that we want to calculate the probability. So x, first of all, random variable, is a number of 1-hour intervals until the first malfunction. And then we will have probability that it will survive 2 hours. It means that this is the probability that x will be greater or equal than 3. Like this. So why? Because it should survive at least 2 hours. It means that the malfunction should be either on the 3rd hour or later. And we can rewrite this probability in a following way. So this is the probability, this is 1 minus probability that the engine will break in less than 3 hours. And now this part can be broken into 2 probabilities. It's either then the malfunction would occur on the 1st hour or malfunction would occur on the 2nd hour. And then I simply apply the geometric distribution formula. So what is the probability that the engine will break on the 1st hour? It's probability of kind of working to the power of 0. So no hours of working times 0.02, which is simply 0.02 right here on the 1st hour. On the 2nd hour, it means that on the 1st hour it works, and on the 2nd hour it breaks. I should have this to the power of 1 times 0.02. And in total, the engine will survive 2 hours. The probability is 96.04%. So again, guys, it's kind of not that difficult. You apply the same multiplication principle as before. You only need to kind of carefully think about the situation. On the 1st hour, it works, and on the next hour, it breaks. That's why we have this. And in general formula, we have something like this. Okay, let me give you an example from here. So let y be just a second. Let y be a number of days until the first stock price decrease. So it's slightly different, right? Because y is a number of days until the first stock price decrease. So find the probability that the stock price will drop on the 5th day exactly. So it means that stock price will be increasing 4 days in a row. So try yourself to calculate this probability. The probability that the stock price will drop on the 5th day exactly, and 4 consecutive 4 days before the stock price will be increasing. Based on this data, based on this information from the previous exercise, that we know that probability that the stock price will be increasing is 0.55. So, any ideas? What's the probability that y will be 5? Guys, anybody? At least some answers if you have. If not, tell me what's the difficulty. What should I explain?
Sorry, I had some problems with internet during the lesson. So could you please explain the formula again, like this probability, how to solve this?
This one? This one?
The exactly like the previous example. So I didn't catch it.
Well, this you mean?
I mean the formula. Yes. So a formula, for example, you wrote the probability of what was it? D.
Here?
Yes.
This one. This is
This
just
one.
a simple application of multiplication principle, and you need to apply this multiplication principle here as well. Look, which sequence of increases and decreases? So maybe I should be a bit more formal here. Maybe I should write like something like denote D, an event that stock price decreases on a particular day, and denote I, an event that stock price increases on a particular day. So, okay, now, Vlad, you will explain yourself this. Which sequence of D's and I's is associated with this situation here? So we want
should have 4 I's and D.
Yes, we want 4 I's and D. Now, what is the probability of this sequence to observe 4 I's and 1 D? If we know that the probability of increase is 0.55 here.
It will be 0.55 in the power of 4, right?
Yes, 4 times like 0.55 first day, 0.55 second day, 0.55 third day, 0.55 fourth day, and then what? And then exactly
then
on the 5th day, it decreases 0.45. And that's a probability that we want to calculate. Exactly this.
Is this the whole formula?
Which formula?
Like, is this the whole formula? Do we need something else or no?
Wait. So first of all, we need to remember multiplication principle. That's it. But now look, this formula on slide is a general formula for any number of x. So here we have a particular number which is 5. On the 5th day, I want to observe the stock price decrease. Now, what if we want to know the probability that stock price falls exactly on, let's say, 10th day? What should we do? We should apply the same principle, but now we need to multiply 0.55 9 times and then multiply by 0.45, right? So it's going to be probability of y equals 10, and it's going to be the same as the probability of I 9 times and d, which is what? Which is 0.55 to the power of 9 multiplied by 0.45, which is here. Now, the question is, how can we write the general formula for any case like this? And here is the general formula. What are we doing? We are taking 1 minus p, when 1 minus p is the probability of failure. In our case, failure is stock increase, because we really need to understand what the failure for this situation. So for this situation, we want to observe stock decrease. That's why failure for us is stock increase. And here is this 0.55 to the power of 9, because x is 10, right? 10th day, the stock price goes down. So it's 10 minus 1, which is 9, right? And I multiply this by 0.45, which is the probability of stock price decrease. So this is just a general formula for any number of x that I want. And this is the example how you can deal with the situation when you even don't know this formula, but you know the multiplication principle and you understand the logic of the situation. And here the same story was, the same multiplication principle was applied, but now we don't have a particular order. In the binomial distribution, you don't have a particular order. You want to know what is the probability of observing 1 increase out of 5 days or 2 increases out of 5 days. That's the same story. That's why we have all these powers here and these multiplications. And the general formula looks like this. Okay, so I hope that during the exercise session you will make it more clear, I hope. So let's stop here. We still have hypergeometric and Poisson distributions, so we will discuss them on the next week. No worries, similar principles are applied. So once again, let me remind you, you have 2 home assignments from tomorrow to the next Friday on the set theory, on the probability. The lecture is here. I will change something in the slides and I will update this file. I hope that's it for today. More questions, concerns, objectives? Okay, then let's have 15-minute break and see you on microeconomics. Don't turn off the meeting, so we will have it here.